Hey everybody, in this video what we're going to be doing is we're going to be talking about the rates of growth of functions. Something similar to what we were doing back in chapter 1 with limits, it's just that we are now going to be able to talk about all types of functions instead of just polynomials. So sometimes we want to know the growth of two functions without graphing them, and so we can do this by using limits and, if necessary, L'Hopital's rule. Now I mentioned that we had done something like this back in term 1, and specifically chapter 1, and so we were doing stuff like this. We had a limit as x went to infinity, and we would have said, well, here's one function, and then here is a second. And what we wanted to do back then was we wanted to know the value of this limit. Well, we learned that by looking at the degree of each polynomial, and since the one on top was larger, that meant then that the top was going to grow faster than the bottom, and we determined that the value of this was going to be infinity. Now what we're going to do is we're going to move on to other types of functions as well. So you're going to be asked a similar question. It's just that this time you might be asked for between e to the x and x squared, which one is going to grow faster? And so the notes here are going to tell you the answer to that question. So the first thing is that we need to be able to define our different types of growth. So the first one is, and I'm dead serious, it is called little o. So this is the official definition up here at the top. F of x is of smaller order than g of x when a function f of x grows slower than a function g of x for large values of x, such that, and then we get to these two limits here. And I want you to know that down here is a much simpler definition for it. Pretty much what you need to know is that our limits, f of x over g of x as x goes to infinity, needs to go to 0. Or, the other one, this limit of g of x over f of x has to equal infinity. When that occurs, we get these results here, that g of x grows faster than f of x, or the official phrasing that we say, f of x is of smaller order than g of x. I'm sorry, there's a lot here on this slide. I apologize if it's really confusing. The last part then is that we have our notation here, and we read this out loud is f is little o of g. So what this is going to look like then, or I'm sorry, we don't have examples yet. We actually have to get to the other definition first. Big O. So if there was a little o, there is a big O. So this one then, f is at most the order of g of x if for large values of x. Both f of x and g of x are positive, and we get this limit is equal to some value of L where L is less than infinity. Pretty much what this is just saying is that L is a constant, and that constant is neither 0 nor infinity. So that's what this is trying to tell us. So pretty much the two things that we're going to have is that for little o, our values are supposed to be either 0 or infinity, and to show that something is big O, we need to show that we get some constant, some non-zero constant L. And then just down here at the bottom, that notation there is telling you that f is big O of g. All right, now we have to get into the examples. So in this first one, we are told to consider y equals x squared and y equals x cubed plus 2x. And what we're supposed to do is we're supposed to show that f is of little o of g. So going back to our definition, that means that we either need to show that f of x over g of x, its limit will become 0, or we need to show that g of x over f of x, its limit is going to go to infinity. For this one, I'm just going to choose g of x over f of x. So we're going to show, so just like what I said, either we're going to show that this limit equals 0, or we're going to show the other limit is going to become infinity. And what I said was, I'm deciding that I just feel like doing that one for right now. So what that's going to look like then, we're going to take our limit as x goes to infinity. We're going to put x cubed plus 2x on top. And we're going to put x squared on bottom. And remember, we want to know, is that going to become infinity? Because if it does, then we have shown that f is little o of g. All right, so the first thing, we need to put in infinity for both of these, and we're going to get infinity over infinity, so we need to do L'Hopital's. Therefore, we're going to get 3x squared plus 2. Down on the bottom, we're going to get 2x. We do L'Hopital's again. We still get infinity over infinity. We're going to have to do L'Hopital's again. We get this time 6x over 2. And when we put in infinity, we get infinity over 2. We get infinity. And I put a check mark there to show that, yes, we did prove that f is little o of g. All right. So for this one then, this is a question from the Thomas book. What I want you to do, show that e to the x grows faster than x squared as x goes to infinity. So pause your video then, try this on your own. When you are done, I will show you how to get the answer. All right, now that you have tried that, so because e of x is going to grow faster than x squared, this one is also going to be an example of little o. So like we did before, if we want e to the x to grow faster than x squared, then let's put e to the x on top. If we put in infinity for both, the top is e to the infinity, the bottom infinity squared is just infinity. All right, we've shown that we're going to get infinity over infinity. We need to do L'Hopital's. Derivative of the top is going to be e to the x. The bottom is going to be 2x. When we put in infinity, we once again get infinity over infinity. We need to do L'Hopital's again. Still e to the x on top. On the bottom now we get 2. And therefore, we show that we get infinity over 2. And we can get infinity. So yes, you could either write e to the x equals little o x squared, or yes, e to the x grows faster. All right. Now what I want you to do is this one as well, show that natural log of x will grow slower than x squared as x goes to infinity. So once again, pause the video. When you are done, start it up again, and I will show you how to do this question. All right, so this time I'm going to do it a little bit differently. If we're supposed to show that natural log of x is going to grow slower than x squared, well, we need to show then that either natural log of x over x squared is going to go to 0, or x squared over natural log of x is going to go to infinity. So when I said I was going to do something different, this time I'm going to show that it's going to go to 0. So I'm going to put natural log of x on top. I'm going to put x squared on bottom. I'm hoping that I can get this to be equal to 0. So the first thing we put in infinity to each of them, well, the natural log of infinity is infinity. Infinity squared is infinity, so we're going to need to do L'Hopital's. The derivative of the top will be 1 over x. On the bottom we get 2x. And this time when we put in infinity, now this is not an indeterminate form. 0 divided by anything is supposed to be 0, and anything divided by infinity is supposed to be 0 as well. So that does end up being 0. We have shown what we were supposed to show, and therefore then we have natural log of x is going to be little o of x squared. Or natural log of x grows slower. And actually, now that I think about it, I'm going to come back here because I think I wrote that wrong. Back from this part here, the slower part is supposed to be first, and then the faster part is supposed to be bottom if it goes to 0. So notice how then that this was f is little o of g. I just realized now for this one that I wrote these in the wrong spot. Those should have been x squared is the slower one, e to the x is the faster one. There we go. That now is correct for that one. And this one we have a similar answer as well. L of x is the slower one, it's on the left. X squared was the faster one, it goes on the right. Okay, so this time then what I am going to show you is that natural log of x is little o of x. So this is telling us then natural log of x is the slow function and x is going to be the fast function. So we're going to go ahead then and make our limit. For this one then, when we put in infinity, we see that we do get infinity over infinity. We need L'Hopital's. We're going to get 1 over x over 1. And kind of like the last one that we just had, this time we are going to get 0 over 1. So that is going to be equal to 0. All right, now we're switching gears. So this time we want big O. And I know it says activity. I actually should demonstrate to you how to do this. So I'll do it. So this time, going back to our definition from earlier, when we are trying to show big O, we want to show this, that L is a constant and it is neither 0 nor infinity. So that's what we're going to be looking for here, is that we want to be able to get some sort of constant. We're going to, in this case, it doesn't matter how we set it up. Either one of the functions can go on top. So I'm just going to go in order. I'm just going to put e to the x plus x squared on top. Down on the bottom, I'm going to put e to the x. And when we first evaluate this, we're going to get infinity plus infinity divided by infinity. So yes, that is infinity over infinity. We need L'Hopital's. Then our first derivative on top and bottom, we're going to get e to the x plus 2x over e to the x. This is still going to be infinity over infinity. We need L'Hopital's again. We get e to the x plus 2 over e to the x. That is still infinity over infinity. So we need to do L'Hopital's again. And finally, we get to a point where we have the exact same thing on top and bottom. So those are going to cancel. And we're just left with 1. And because we found a non-zero constant, we have shown then that e to the x plus x squared is going to be big O of e to the x. In other words, these two functions up at the top grow at roughly the same rate. One thing that I could do actually just to kind of demonstrate that to you as well, this is the first time I've tried doing this, I guess. So what we are going to do is I'm going to take you over to Desmos. You can see that I searched a trapezoid recently. And I'm going to graph both of these functions. So we have e to the x, I'm sorry, that's squared. I want x. There we go. And then it's going to be plus x squared. And then the second one is going to be e to the x. Can't find the e. There it is. So what is supposed to happen is that we're saying that these are growing at roughly the same rate. So here's what the two functions look like. We have a parabola, and then we also happen to have the curve e to the x here. And then as we follow both curves, they're looking pretty parallel. And actually, it appears as though they're getting closer and closer the further that we go up. And so that shows, or maybe that's because I'm, sorry, I guess I'm actually squeezing it together, I suppose. That's probably why they're getting closer. But you'll notice that these are growing at roughly the same rate. And so that's what's happening with the big O. Meanwhile, something different, let me just show e to the x and x squared. So there's e to the x. Oh, I probably would have been... I didn't do that the most efficient way, but oh well. So in this case, so here's our two graphs, and then as we start following them up, you notice that they don't appear to be parallel. The red line is going at a steeper rate than the blue line is. The blue is x squared, the red is e to the x. So this visually is showing us that e to the x is growing faster. So that's just kind of what we've been doing here with little o and big O, just so you're aware. Okay, so that is the last... Oh, I only had one of those? I'm sorry. I guess I need to put in more of those for the future. Well, okay, so here is the homework then. Again, go to Schoology to see which ones are required and which ones are optional. Thank you for listening, everybody. Have a good day.